In a vast universe that we cannot understand, the idea of destiny has long fascinated people. It transports us to stories of apocalyptic events, where the world collapses into a fiery landscape, satisfying our deepest fears and longings for the unknown. Science fiction, with its dramatic depictions of the end of the world, often makes us think of a tragic end, when everything we know is swallowed up by the emptiness of life. But what if the end of the world is not a terrible blow, but a smooth and invisible transition to a new beginning? The James Webb Space Telescope, our last eye on the universe, has made a revelation that challenges everything we thought we knew about the end of the universe. According to this groundbreaking discovery, the universe may no longer be expanding. This knowledge has great implications, suggesting that we are on the verge of the birth of a new world, one that mirrors the beginning of the universe. Welcome to Explore Big Bang 2.0. The end of the world is not an apocalypse, but a return to the beginning. Over the years, scientists have held on to the idea that the universe is expanding, a theory that has shaped our understanding of the universe. The idea that the universe is expanding and that galaxies are moving has been a cornerstone of astronomical research since the early 20th century. But what should this priority be? The James Webb Space Telescope has provided data indicating that the universe has stopped growing. This amazing revelation turns our thinking upside down and forces us to rethink the structure of space and time. Imagine a world that has not evolved, a world where the laws of physics as we know them begin to emerge. The effects are spectacular, suggesting that the end of the world will be like its beginning, not a violent end but a slow, circular process. Are we on the brink of another Big Bang, a global rebirth that will shatter all our expectations? The Big Bang theory is an important step in our understanding of the origin of the universe. It all started from a singularity, a hot, dense place, where everything, energy, space and time was compressed into one place. About 13.8 billion years ago, this special form began to expand in what is known as the Big Bang. Contrary to popular belief, the Big Bang was not a literal explosion. It was an expansion of space itself, that caused the universe to grow from something smaller than an atom to something larger in a fraction of a second. Due to the speed of this consumption, it was 90 times the size of the universe at one time. In the first second, the universe cooled enough to form subatomic particles, the building blocks of matter such as protons, neutrons and electrons. These particles eventually joined together to form atoms, resulting in the formation of stars, galaxies, and all the structures we see in the universe today. Our understanding of the Big Bang is supported by several important lines of evidence, the most important of which is the cosmic microwave background, CMB. Discovered in 1965, the CMB is the slowest of the Big Bang, a tiny glow that fills the entire universe and serves as a snapshot of the infant universe. Radiation is a view of the universe as it existed only 380,000 years after the Big Bang, when it was still a hot, solid plasma. The consistency of the CMB across the sky is a strong indication that the universe started from the same place. In addition, the redshift of distant galaxies, discovered by Edwin Hubble in the 1920s, indicates that galaxies are moving away from us, supporting the idea that the universe is expanding from its beginning. Despite the strength of this evidence, our understanding of Earth's past remains largely speculative, relying on mathematical models and simulations that attempt to recreate the conditions of the past. Big Bang launched in December 2021, the James Webb Space Telescope, JWST, is designed to look deeper into the universe than ever before, including the Hubble Space Telescope. With its advanced infrared capabilities, JWST will be able to observe the oldest moon in the universe, the moon that traveled more than 13 billion years to reach us. This allows scientists to study the formation of the first stars and galaxies, revealing the history of the first universe. One of JWST's greatest contributions is its ability to measure the universe's expansion rate with great precision. By observing distant galaxies and their redshifts, JWST has provided data that challenges long-held beliefs in the universe. New evidence suggests that the rate of expansion is slowing or, worse, has already stopped. The idea that the universe might not expand is both fascinating and terrifying. If expansion has stopped, it means that the world has reached a critical point in its development. This may mark the beginning of a new phase in the life cycle of the universe, which may lead to collapse or rebirth. The cessation of expansion will have important consequences for our understanding of the universe. These current models challenge global catastrophes, including the Big Freeze, Big Rip, and Big Crunch. All these phenomena depend on the continued expansion of the universe, but if the expansion stops, then a new theory may be created to explain the universe in the future. Could the universe be facing another great explosion, a revolutionary process in which the universe was born, expanded, contracted, and reborn in an endless loop? The JWST data opens up such possibilities and forces us to reevaluate everything we know. While the JWST data is groundbreaking, it also reveals the limitations of our current understanding of the universe. Much of what we know about the universe is based on theoretical models that are subject to revision as new evidence emerges. The discovery that the universe is no longer expanding is a reminder that our understanding of the universe is still incomplete, and that there may be aspects of reality that we have yet to discover. The world is a vast and complex system, and our ability to understand it is limited by the limits of human perception and imagination. As we continue to explore the world, we must be open to new ideas and willing to challenge our deeply held beliefs about the nature of reality. The discovery that the universe has ended is only the beginning of a new era of civilization. As scientists continue to analyze the JWST data, they will undoubtedly discover more surprises about the nature of the universe. These findings lead to the development of new theories and models that will shape our understanding of the universe for years to come. The end of the world, once thought of as a distant and unknown event, may be something we can study and predict. As we look to the future, we must be prepared for the possibility that the end of the world will be different than anything we imagine. One of the most perplexing aspects of the modern universe is the role of dark energy, a form of energy believed to be responsible for the universe's acceleration. Dark energy was first proposed in the late 1990s to explain why distant galaxies seem to be moving away from us faster than previously thought. This discovery led to the widespread belief that the universe would continue to expand indefinitely, and that dark energy was driving this acceleration. However, new data from the James Webb Space Telescope has cast doubt on this hypothesis. If the universe has stopped growing, it raises important questions about the nature of dark energy. Is dark energy not as strong or stable as we once thought? Maybe it's not a constant force, but something that changes over time and eventually weakens if it can't keep up with the expansion. Dark energy can eliminate or reverse its effects and open up new avenues of research, which could change our understanding of the end of the universe. The idea that the universe can stop expanding or contracting has a profound effect on our understanding of time. In the context of the wider world, it is often considered a one-way street, moving from the Big Bang to the end. However, if the universe is entering a phase where expansion ceases or reverses, time could take on a cyclical nature, similar to the universe's own potential cycles of birth, expansion, and contraction. This idea challenges our linear perception of time and suggests that what we experience as the passage of time might be far more complex than previously imagined. In a universe where cycles of Big Bangs and Big Crunches are possible, time could loop back on itself, creating a reality where past, present, and future are interconnected in ways that defy conventional logic. Such a perspective not only alters the scientific view of the cosmos but also has profound philosophical implications, prompting us to rethink our place within this ever-changing universe. The idea that the universe might stop expanding has forced scientists to revisit old theories about its ultimate fate. Traditionally, there have been three primary scenarios: the Big Freeze, the Big Crunch, and the Big Rip. The Big Freeze, where the universe continues expanding until all stars burn out and galaxies drift apart, leading to a cold, dark cosmos, has been the prevailing theory for decades. The Big Crunch, a scenario in which the universe's expansion slows, halts, and eventually reverses, pulling all matter back into a singularity, was largely dismissed once the acceleration of expansion was discovered. However, if the universe is indeed slowing its expansion, the Big Crunch could be back on the table. This reintroduction of the Big Crunch not only revives discussions about a cyclic universe, where Big Bangs and Big Crunches occur in endless succession, but also raises the possibility of a Big Bounce, where the universe contracts to a point before expanding again. These renewed speculations offer a fascinating glimpse into how our understanding of the cosmos could shift dramatically based on new data, challenging long-held beliefs and opening up possibilities for new theories that could redefine cosmology. As we delve deeper into the potential halt of the universe's expansion, the role of quantum mechanics in cosmic evolution becomes increasingly relevant. Quantum mechanics, the branch of physics that deals with the behavior of particles on the smallest scales, has always had a complicated relationship with general relativity, which governs large-scale cosmic phenomena. If the universe is indeed transitioning from expansion to contraction, quantum effects could play a significant role in this process. For instance, quantum fluctuations in the early universe are believed to have sown the seeds for the formation of galaxies and other large-scale structures. These differences can also affect the world's situation towards a new phase, whether it is a phase of expansion or a revolution. Some theories suggest that quantum entanglement, in which particles are connected so that one form is always in contact with another, may be a universal form, related to the macrostructure. And the end of the world. Cross.